He hasn't. So, I just checked with the ride.
So my mom's from Shanghai,
Yeah.
and my dad's from
Yeah, I asked any.
Wuhan.
Okay.
So COVID originated actually, but it's like southern parts of China. Oh, okay. Oh, okay, yeah. I really haven't been traveled in Taiwan before. I've only been through.
Achieving stable operation of Flora for flight, to validate HREXI's spaceflight.
Oh my gosh, spoiler!
Spoilers, sorry.
Yeah.
I hope you won't be upset, but I had
No,
to.
it's perfect.
There you go. If I can't answer any questions, you can help me.
What? No.
Wow. Sounds good. Oh no, he'll know if I'm saying anything wrong. Sure.
Could you start at 140?
Yes. Yeah. I'm good whenever.
Okay, Sean, we should start. Yep. You're all set. Let's go to the mic here.
Oh yeah, should I turn?
No.
Oh, I think here. Oh.
Good. Can you hear me? Can you hear me? Can you hear me? Yeah. Okay, very good. So welcome to the senior thesis presentations. As you all know, by now there are 6 brilliant students going to be presenting their work this afternoon. My role has been I'm not quite sure what my role is, but it's keeping everybody on schedule, which is a good thing for me to do today. The purpose of the senior thesis is to introduce the student to research with a significant amount of independence is required, and to give them something to use to further their career, because this is a group of people, most of whom are going to go to graduate school right away. One thing that struck me is that I think the range of types of project that people are involved in has been improving in a very interesting way. We've got people who worked in the lab, work on technical evaluation of critical materials and subsystems. We've also got people who've done very significant analytic work and very significant simulation work. So I think it's going to be a good afternoon. I encourage you to stay for as long as you can. I think that clock is probably wrong. So what is the time? 1:33. Well, we could get you started. But one thing, if we do get out of order a little bit during one talk, I will not move the whole program up, because some people are coming to this session for particular talks, and they should be able to rely on the start time given in this document here. But as is commonly the case, I speak for less than I'm invited to, even when I wrote the invitation. So I think I'll give a little bit of a head start to Qijia. This is Qijia Zhou. She's a senior concentrator in astrophysics. And she's been working on an extremely interesting project called Ghost in the Machine, characterizing the Viaspec binary transmission diffraction grating. Go ahead.
Okay. Is my mic on? Yes. Okay, awesome. Yeah, thank you very much, again, everyone, for coming to the senior thesis presentations. I'm really excited to talk about, again, characterizing the Viaspec binary transmission diffraction grating today. And of course, I'll explain what that mouthful is shortly, and of course, explain exactly what the ghost in the machine is. I'm advised by Dr. Dan Fabricant and Dr. Charlie Conroy. All right, so starting from just like the basics, diffraction gratings and why they're interesting to astronomers. So first of all, astronomers love spectra. I'm sure everyone knows this, since, again, an object spectra can tell us about its chemical composition, distance, velocities, and other interesting properties that we'd like to know. Astronomers use instruments called spectrographs to split light into its component wavelengths to look at object spectrums. And most astronomical spectrographs use diffraction gratings as the main dispersive element. So here's a very simplified schematic of a spectrograph with a diffraction grating, where we collect the light from a star using our telescopes. It passes through the diffraction grating, it gets dispersed, and we can collect the spectra, so the component wavelengths, on our detector. There are many different types of diffraction gratings. And one thing that they all have in common, in fact, what sort of defines a diffraction grating, is some sort of periodic structure. So the periodic structure in the grating introduces systematic changes in the light path, which cause different wavelengths of light to get diffracted at different angles. So these first two diffraction gratings, the blaze relief grating and the volume phase holographic, or VPH grating, are the most commonly used gratings in astronomy. So with the blaze relief grating, we have this periodic sawtooth pattern that disperses the light. And usually blaze relief gratings are most efficient in bluer wavelengths, though they are limited to lower dispersion, so usually used just for lower resolution spectrographs. VPH gratings are a photographic emulsion that has sinusoidal variations in refractive index. So like in the emulsion, and it's sandwiched between two pieces of glass. So that variation in refractive index is what causes the dispersion. VPH gratings are good at high dispersion, so high resolutions, and they can be tuned to be used at a variety of wavelengths. However, VPH suppliers are becoming increasingly difficult to find since the demand in the industry for these types of gratings is decreasing. So we're currently looking into alternatives to these types of gratings. So in this project, we introduced binary gratings. So binary gratings use these periodic etched grooves to disperse light. And this has been used in a lot of different applications in physics, but not very much, it's not really been widely used in astronomy yet. So in this thesis, I'll be characterizing a binary diffraction grating for astronomical use. The specific project that will be applying this diffraction grating is the VIA survey. So the VIA survey is led by Dr. Charlie Conroy here at Harvard and Dr. Ono Debiasing at Carnegie Observatories. It will be an all-sky spectroscopic survey of Milky Way halo stars. It'll collect over 2 million spectra with 100 meter per second RV precision. Again, the main science goals of this survey is to, first of all, use stellar streams to study dark matter. So stellar streams are tidally dispersed globular clusters. Again, they form a stream across the sky, and we'll be looking for tiny velocity perturbations in these stellar streams that might be indicative of collisions with dark matter halos. We'll also be conducting dwarf galaxy follow-up from LSST. So LSST will provide some photometric data and VIA will be able to provide spectroscopic follow-up using kinematic data on dwarf galaxy membership. And finally, we'll be able to look at cold gas in the Milky Way by using this whole catalog of stellar spectra as, again, like backlights for a cold gas. And for this survey, we'll be building 2 different spectrographs, so Viaspec, one for the MMT and one for the Magellan clay. And binary gratings will be the main dispersive element in both spectrographs. And one of the reasons that we're considering binary gratings for VIA is because of this projected performance between VPH and binary gratings. So again, from simulations, we're able to see that we predict that binary gratings will be overall more efficient, especially at the spectral extremes when compared to VPH gratings. And this is especially important for VIA since the magnesium V triplet and the NAD doublet are both sort of in the spectral extremes of the range that we're looking at. So where my project comes in is characterizing this binary grating. Again, because it's very new to astronomy, this type of grating hasn't been well characterized for astronomical use in spectrographs. And we want to verify that there aren't any stray light features or so-called optical ghosts that might compromise our data. Again, these stray light features can arise from different imperfections, again, in the grating manufacturing process, or maybe, again, we might be concerned that there's some inherent stray light from the design of the grating. And in order to do this, we create our experimental setup called monospec. It's a bit of a paradoxical spectrograph. Again, we use a single wavelength of light in this spectrograph. Since this is for simplicity, we're able to characterize all the stray light features in the grating by just testing with one wavelength. Monospec is basically a miniature version of Viaspec. So we have a light source again, to provide some kind of artificial light, and then it'll go through the grating and get focused by the camera optics into our CMOS detector. And using this setup, we want to look for, again, any kind of like stray light feature, rogue light from the grating. So the first part of this project, again, since we expect that these grating features might be very faint, we want to make sure that there aren't going to be any effects from like scattered light outside of the system that could interfere with our tests. So the first part was building the light enclosure. So here we have a time-lapse video of me and grad student Abby White, again, attaching blackout felt to these aluminum panels. These aluminum panels will be the walls of our enclosure, and the blackout felt on the inside will prevent internal reflection in the system inside the enclosure. And here's Abby and I in the VIA tent, constructing and assembling those panels onto our light enclosure frame. And there's Andrew Klein and Joe Zajac, who are also main VIA project engineers, who have really helped us design and build multiple components of monospec. Here's the finished light enclosure. And basically, it's just a giant aluminum box that protects the system on the inside from light from the outside. Next part was constructing the light source. So we use a 543 nanometer helium neon laser. We pass it through a beam expander and a neutral density filter to sort of reduce the intensity of the light. And then it goes through a spatial filter. Essentially what that does is just create a nice, clean Gaussian point source of light. So again, just easy for us to characterize. This next part was assembling the camera optics. So we had a set of custom lenses that help us focus down our light onto the detector. There's a picture of Dr. Conroy and I in the lab cleaning one of those lenses, and then the finished lenses in their tube. And then I was also in the clean room with Joe and Peter, again, to install some other custom optics onto our CMOS camera, as well as a custom baffle. Yeah, I was able to get a lot of really great hands-on experience in the lab through this project. And finally, the most important part, installing the grating. There's a picture of our grating. It's a 6-inch by 6-inch grating, so probably one of the largest diffraction gratings I've seen. Has 2,000 lines per millimeter and a group depth of about 1 micron. And of course, we tested the grating with just like iPhone flashlight, and it does indeed disperse light, which is great. And now moving on, I'll get into our results. So before I start with the results, sort of ideal image that we would get, again, if the grating was performing perfectly, is that, again, we're using a single wavelength of light. So all of that light should be diffracted at the same angle to a single point onto the CMOS detector. So ideally, we get just a dark image with a point of light in the middle. And sort of what we get. So this slide is about the size of like our full image from the CMOS camera. And there's a zoomed in picture of the center where we have this very nice focused point of light in the center. And we don't see any optical ghosts. And so, well, let's try to go brighter and see if there's any fainter features. In this picture, the center spot is already saturated, but we still don't see any features, so keep going brighter. Now the center spot is extremely saturated, but we still don't see any ghosts, so we thought, why not just try to blow out the detector and completely oversaturate it? And finally, we have this like giant, again, oversaturated center, and we finally spot some ghosts. So you can see that they're very faint along this vertical axis. There are these evenly spaced spots. And for reference, again, the dispersion axis of our grating is horizontal. So if we had multiple wavelengths of light going through our diffraction grating, it would be dispersed horizontally. But these ghosts are dispersed vertically, so perpendicular to our main dispersion axis. So that made us think, again, and these are also very regularly spaced ghosts. That makes us think that there's some sort of perpendicular grating feature that's overlaid on top of our main grating. So in order to characterize that, we measure the distance between the different grating, between the different ghosts. And we find that that corresponds to a grating with a period about 12.5 lines per millimeter. So again, a grating with that period would produce ghosts spaced by that length in our setup. And that, interestingly enough, matches the periodicity of the exposure steps during the manufacturing process. So what that means is, so going back to when the grating was manufactured by the Plymouth Grating Laboratories, we start with a substrate. So we want to have, we have a fused silica substrate where we want to etch grooves into them to create our grating. So how that's done is that first that substrate is covered with a layer of photoresist, which is represented by this gray square here. And that photoresist is light sensitive. And in order to create that very precisely spaced line, those precisely spaced lines, we expose that photoresist to interference fringes of light with that same periodicity. So then that photoresist will react to it and form that periodic structure. However, PGL does not have a beam that's 6 by 6 inches. So they have to expose that photoresist sort of line by line. Again, if we have a smaller beam, it'll have to sort of scan across the grating to slowly expose each bit of the photoresist. And again, have those scans stitched together. And again, if that works perfectly, again, if that stitch occurs perfectly, then we get a perfect grating all the way through. But if there's any sort of systematic imperfection or overlap between each scan, we'll get some kind of imperfection at the periodicity of those exposure steps. And again, going back to the definition of a grating, the only thing that we need to create a grating is some kind of periodic structure. So it doesn't really matter what that imperfection is. If it occurs periodically, then it'll create a grating. So we think that this grating, since that exposure step corresponds to the period that we observe from those ghosts, we think the ghosts are just an artifact of the manufacturing process. But what does this mean for Viaspec? Well, luckily, the ghost to main image brightness has a ratio of about 1 to 10 to the 6. So the ghosts are much, much fainter than the main image. And in comparison, VIA's CCDs have a maximum dynamic contrast of 1 to 10 to the 4. So again, the CCDs likely don't have the dynamic contrast to actually capture dynamic range. And again, just to add on, most science exposures will only have on the order of 10 to 100 counts for this survey. So again, with this image, that centers, that main image is super oversaturated. It's much brighter than probably any source that we'll actually observe in the science survey. So all in all, this means that for Via, these ghosts will probably be pretty negligible, and we probably won't even be able to see them. So that is a great big green check mark for this grading for Viaspec. So looking forward, we're happy to say that the PGL binary grading performed extremely well in our monospec testing. And again, looking for Via, that's great news, but also potentially for other future large format spectrographs, binary gratings could be a viable alternative to VPH gratings. Again, there are some limitations. Again, binary gratings are limited to be efficient near when the wavelength of light is close to the periodicity of the grating. So it's a little bit more limited in wavelength range than VPH gratings are. But again, like for Via, it could be more broadband compared to VPH in some wavelength ranges. So we're really excited to see where binary gratings can go in astronomy. And again, before I end off, I just really want to acknowledge my advisors, Dr. Dan Fabricant and Dr. Charlie Conroy, for all of their help in answering all of my silly questions throughout this process. Of course, grad student Abby White, who's here today, she spent many hours with me in the lab, like creating monospec and testing it. And of course, the CFA Central Engineering worked with lots of great engineers, including Joe Zajac, Andrew Klein, Peter Doherty, and machinist Dave Thoreau in the lab. Of course, thank you to the rest of the VIA team. I hope I'll be here when VIA is commissioned and see some of the amazing science results that we produced. All right, thank you.
So thank you very much. So does anybody have any questions for Qijia? Brian?
You found that there was a periodicity in one stepping direction that gave you these perpendicular ghosts. Mm-hmm. If you had errors as it tracks along, I mean, you gave the impression from the size from your animation that in fact they have to build up the other direction as well by a series of steps. So what happens when those steps get out of phase, or are you confident that didn't happen? Is there something particular about the perpendicular direction?
Yeah, that's a great question. I guess if it did go out of phase as it was scanning across, then we would have a lot of errors, because that would affect like the line density of like the grading that we want. And I think that we'd be able to see like pretty significant effects if there were like issues with the 2,000 lines per millimeter spacing. And I think that we would get like some sort of you could get another like different I guess like grading pattern if there's some kind of systematic error that way as well. But it would be in like the main dispersion direction instead of vertical. I think. Good question.
Yeah, Jacob?
What's the benefit of having a grading with high efficiency?
Oh, yeah, that's a great question. I probably should have explained that. So grading with high efficiency means that like more light will be able to like pass through it. These are transmissive diffraction gratings, so the light is dispersed when it passes through the grating. And we want to try to, again, save as many get as many photons to the detector as we can. And if we're losing like photons like in the diffraction grating, then that means we just get less signal when it comes to the detector. That's a great question. Yeah.
Mm-hmm. Brian?
In your main image, there's a substantial halo around it. Is any of that due to the grating itself, or is it in your test setup?
Yeah, that's another great question. I think, are you talking about this one?
Yes.
Or yes. Okay. There is another ghost that I sort of like skipped over for brevity here, but I think that's probably from the LitRo ghost. So because like we're in that like LitRo configuration where the incidence angle is equal to the exit angle, there is probably some light that sort of like reflects off the detector, reflects off like one of the lenses, comes back to the grating, gets like recollimated through, and that causes like an additional ghost that's around like the size of that beam. And I think that like edge is like what we're seeing, but we sort of like aligned that ghost to the main beam since it was like going to be saturated anyways, so it would like sort of be out of the way of the other ghosts that we were looking at.
Any other questions? Well, let's thank our speaker again. That was very clear, very good. Thank you.
Thank you.
Okay, just make a note that we're actually ahead of time, and a significant fraction of that is my fault for just getting started in my enthusiasm to hear from Qijia and her successors. So I think it's important that we keep to the start times on the program to the extent possible. So we've got a 10-minute gap where you can have some tea and cookies if you want, and we'll start the next one, who is Jacob, at 2 p.m. Thank you very much. I'm going to go get my phone.
Okay, yeah, sounds good.
Thank you. But thank you, that was very reassuring. I'm going to go and get my phone, so I'm going to be out of the room for 5 minutes.
Yep, no worries.
Can you hear me? Yep. Okay, very good. So our second speaker is also doing an instrumental project. This is Jacob Buehler, one of our seniors this year. He's been working with Brandon Allen and Josh Grindley, and the title of his talk is Environmental Testing of HREXI, Assessing CZT Detector Performance for Spaceflight in the Thermal Enclosure. Thank you.
All right. Good afternoon, everyone. My name is Jacob Buehler, and today I'm going to be talking about environmental testing for the HREXI X-ray and gamma ray monitor, and a new dashboard for performance monitoring that I'm developing for it. So firstly, I want to start off by giving some background information. Gamma ray bursts were first discovered by the Vela program, which was launched in 1963 by the American Department of Defense. Originally designed as a way to detect illegal nuclear tests here on Earth, Vela satellites ended up detecting numerous bursts of X-rays and gamma rays coming from space. In the following decades, gamma ray bursts have become critical to advancing our understanding of extreme physics, such as the mergers between neutron stars, black holes, and white dwarfs, to our understanding of the history of nucleosynthesis in the universe, and to our understanding of supernova mechanics. X-ray and gamma ray imagers like HREXI are key for imaging high-energy phenomena. Currently, the Neil Grell's Swift Observatory is the preeminent X-ray transient monitor. Next, I want to talk about HREXI itself. HREXI stands for High Resolution Energetic X-ray Imager, and it is meant to be a space telescope detecting energetic transients, such as gamma ray bursts or supernovae. Swift localizes gamma ray transients and then enables and conducts follow-up observations, but this process takes time. HREXI can both localize and image targets in a single step, thus allowing for more complete measurements that do not cut off the first portion of the event. Like Swift, HREXI uses coded aperture imaging for wide-field monitoring. HREXI evolved from ProtoExist-2, which was first tested in a high-altitude balloon in October 2012, achieving stable operation over a 7-hour flight and helping to validate HREXI's reliability for spaceflight. HREXI has a potentially much higher angular resolution than Swift due to its larger number of detectors and smaller pixel size. So HREXI uses cadmium zinc telluride, or CZT, detectors. These were first used in major capacity in Swift. And its main benefits are that it effectively dissipates high-energy photons due to its high band gaps, that it functions at room temperature, and that it is easily commercially manufactured. In order to function, a voltage bias is first applied at the cathode. When a photon strikes the detector, a cloud of electrons is released, and the voltage bias causes these electrons to migrate to an ASIC chip, which uses the number of electrons recorded as a proxy for photon energy. The CZT detectors on HREXI use a 3 millimeter thick CZT layer as opposed to the 5 millimeters on ProtoExist, which has the effect of reducing background noise. Each detector has 1,024 pixels in a 32 by 32 layout. The first objective of this project is to verify the safe operating temperatures of the HREXI CZT detectors. The second is to create the HREXI Event Viewer dashboard. So the Event Viewer works as follows. A command line action is given, which triggers the data acquisition routine. This both sends data to the disk to be saved as a file, but also sends chunks of data to a processing routine, thus extracting the energy spectrum, the pixel map of events, and header data. These are converted to JSON format and then sent to a port to be accessed by the client, which uses JavaScript to create interactive charts within an HTML dashboard. This is useful for easily understanding how the detector is performing in real time. And here is a visual demonstration of what the Event Viewer looks like in action. And on the top left, you can see housekeeping data being plotted. On the top right, you can see the measured energy spectrum being integrated. On the bottom left, you can see the pixel map of events being integrated, which actually shows damage to the detector that recorded that data. You see in the bottom right corner. And on the bottom right is a button to reset all of these plots. Oh, my bad. The experimental setup for thermal testing was, as is demonstrated on the right-hand side. We used an americium-241 source with a photo peak of 59.5 kilo-electron volts and an activity of 9.9 millicuries. The thermal chamber was flooded with 50 liters of room temperature nitrogen per minute. On March 19, the temperature was gradually lowered to negative 20 Celsius, and on March 20, the temperature was gradually increased to positive 40 Celsius. We used thermocouples to measure the temperature of the detector, the chassis surrounding it, and the chamber. and ran a pulsar scan continuously to validate the health of the ASIC. Now, what a pulsar scan is basically a fake event that is created by injecting charge into the front end of the ASIC, which actually integrates in the same way that a real event would. And this is useful because it creates simulated events in a way that is easily identifiable so that its signature is easily recoverable later on. And here we examine the evolution of the americium-241 spectrum over the course of low temperature testing, demonstrated here by the heat map on top. So the x-axis corresponds to time, while the y-axis on the heat map corresponds to energy, and the color on the heat map corresponds to the number of counts at that energy for that time bin. So the americium emission line is indicated by the pink horizontal dotted line you see right there. The middle plot indicates a count rate as a function of time, and that's just overall counts for all photons. And the bottom plot indicates the temperature as a function of time. Both of the blue line shows the chamber, and the other two lines show the actual detector itself. And you can see that when the detector gets below about -6 degrees Celsius, so right around here, the americium signal actually gets a lot weaker, so you can't see that signal anymore. We also see that it gets much stronger right around here once the detector starts warming up again. We also see that the count rate appears to be slightly higher for Here we examine the evolution of the americium signal over the course of high temperature testing. Again, we see that when the detector temperature is lower than about -6 degrees Celsius, the americium signal is a lot weaker. Additionally, when the detector is warming up, the count rate is extremely high, as indicated by the 3 spikes right in the middle of the plot when the detector is warming up, as indicated by this plot on bottom. We also see that the count rate appears to be slightly higher for detector temperatures more than 20 degrees, but please note also that the source was actually moved slightly after 12:38 p.m., so that's not too strong of a finding. In this slide, we examine the evolution of the pulsar signature during low temperature testing. And this is actually really important because the pulsar signal is both created and recovered by the ASIC, and is unaffected by the CCT layer, so it's actually a really effective way to separate the CCT effects from the ASIC effects. And we actually see similar patterns as we do in the americium signal, such as signal weakening at low detector temperatures, kind of at this time, and then high count rates while warming up. You see that right around here, especially, this big spike. And actually, if we look at the pulsar signature during the high temperature testing, we observe the same patterns. Toward the beginning of the scan, we see a period of low detector temperature right around here, which actually corresponds to a really low count rate from the pulsar signature. And this actually could suggest that low detector sensitivity at low temperatures is due to ASIC issues, especially since the ASIC itself is actually only rated to perform down to -5 degrees Celsius. Also, note the 3 steps in the middle of the scan where the detector is warming up, which corresponds to 3 spikes in the count rate right here, which is weird because the pulsar count rate should be constant. We didn't change anything about the pulsars throughout the entire scan. And actually, one hypothesis for further research is that the pulsar count rate may actually be related to the rate of change in the detector temperature. So this project is important because space telescopes must be reliable. This is because they are far beyond the reach of physical manipulation, and it is nearly impossible to repair them if they break down. Consequently, it is critical to understand the physical characteristics of the HREXI detectors because space is an extreme environment. Additionally, the event viewer now allows scientists to evaluate the performance of the detector in real time in a way that is lightweight and easy to use. And actually before, if you wanted to evaluate that performance, you would have to load an incomplete file during a detector scan, parse it, and then process it manually, which is really cumbersome. So the primary result is the testing of a CCT detector at different temperatures. It was found that the detector loses sensitivity at temperatures below -6 degrees Celsius, which may be due to a loss of functionality in the ASIC. Additionally, a possible link between ASIC sensitivity and not just the temperature of the detector, but also the rate of detector temperature change was observed. So the dead time calculation is still in progress. And a secondary result is the creation of the HREXI event viewer. And the next step for this project is the presentation of this work at AAS 244 in Madison, Wisconsin. So this project was a collaboration between a great number of people. And I would really like to express my deep thanks to the following for their constant support. Brendan Allen, Josh Grinley, Jason Hong, Charles Alcock, all of the staff at MIT Lincoln Laboratory, Ralph Kraft, and my fellow students in Astronomy 99. And that's all.
Okay, this talk is now open for questions. Ryan.
In your high temperature plot, there was a section in the middle where the gamma-rhenium signal completely disappeared suddenly. What's going on there?
Yeah, for sure. So actually, that was a lunch break taken between 11:38 p.m. and 12:38 p.m. by the Lincoln Lab staff. We all kind of, I'm not part of Lincoln Lab, so we all had to exit the actual testing room, and they didn't want to have just a radioactive source kind of hanging out with no one to take care of it. So it was taken out during that time, and that was replaced after 12:38 p.m.
So what's the scale of spacecraft that this is intended for? Is it a small satellite or a large satellite like Charlie?
I think Proto exists 2. It was a pretty large satellite. I think Proto.
It's a balloon flight.
Yeah.
You can come down to the lab, Charles, and we can show you the detector chamber, which is still in our lab.
Okay.
But it was a balloon flight that I think you watched. No,
Yeah,
you weren't here.
remember that.
Of course you were here. I'm listening.
Okay, thank
It's
you.
a balloon mission.
So I can really quickly, so Jacob,
Small sat.
small set, so about the size of a mini fridge.
About the size of a mini fridge.
Or a washing machine, roughly that scale. That's what our specs proposal is all about, with the 2 of those. It's the reason for this development. A very minor correction on your opening statement about the Buehler satellites. They were not to monitor nuclear explosions on the ground, but rather in space, because the test ban treaty had been recently signed with Russia, and nobody believed that they would hold to it. So when flashes of gamma rays came in the sky, the Los Alamos crowd got very excited. This is what they're looking for. A nuclear explosion is very rich in gamma rays, and it's a flash. So, my God, what's happening? Well, then other flashes were detected, and on over the 2 years plus. So they clearly weren't due to the Russians setting off explosions everywhere. And it wasn't until the 1990s that with the Compton Gamma Ray Observatory that enough bursts were detected to be demonstrated to be completely isotropic on the sky. And that started a great debate whether we're in the galactic halo, cosmological distances, and the latter one. Sorry for all the words, but I just wanted to supply some more initial conditions.
Thanks, Professor.
Okay, do we have any other questions for Jacob? Okay, so we're going to, oh, sorry, please go ahead, Brandon.
I'm going to ask you a question that we discussed, so I hope you remember. But what happens? So one of the questions went to what happens around 1400, where you see that dip in source events, right?
Mm-hmm.
I think that was what was asked. What happens when you have hot pixels on the detector?
So basically, there's a concept of dead time. Okay, so firstly, basically a hot pixel is any pixel that is kind of erroneously detecting thousands of events at once, and kind of even if those events don't really exist. And basically, that's a problem because there's this idea of dead time. Basically, what dead time means is that immediately after you detect a photon, the detector actually won't detect anything for a very short period of time. But if you have a hot pixel that's just erroneously reporting millions of events, even if you have an actual signal like this, you're gonna not measure a real signal. Like the M-RESIM signal was still there when this hot pixel occurred, but because of the dead time, the detector was just being blown out and just wasn't recording anything.
Right, great. And then are you going to look at the effect of hot pixels as a function of temperature? and your remaining time?
Yeah, I mean, I think that'd be definitely a very worthy thing for us to look at. I think definitely like on March 19, right? We had a ton of issues with hot pixels, and I think it'd be really great to find a way to solve those.
On your energy scale here, you have at 400 ADU, you have your primary signal, but there's also a peak at 250 and a peak at 175. What's causing the multiple energy? Do you know?
I think some of the pixels are being. I'm not sure.
So Jacob, remember your source has the main peak. What are those lower energy you're talking about?
Oh, are those more secondary peaks? Like, okay, I guess those are also parts of the Emerson
So part of the
spectrum.
actual Emerson. Cool. Okay.
But the relative strength of them changes throughout the test, which is interesting, right?
Yeah.
The brightness of the middle band is absent and then becomes very strong. The brightness of the weakest, lowest energy band is present. And so is that a big temperature dependence?
Kind of looks like it does. I guess we haven't really looked at that.
So I'll just add, I'm actually very interested in whether or not that is a real thing. But yeah, you're right. It does look like it has some changes in temperature, which goes into the efficiency question as you go across the energy band. So that's a neat discovery out of this. I'm not going to wave my hand and say it's a discovery, but that's what we're looking at. It's an interesting effect.
Okay, thank you. I think we've. Do we have any other questions? Okay, so we're going to keep the schedule. We'll start the next talk at 2:20, which is a little over 3 minutes away. Thank you. Thank you very much. So we'll start on the clock.
Question, is there a Zoom link for this? Is there a Zoom link for this? Oh, okay.
Okay. How do I go back? Here we go. Okay.
You're muted now. We'll unmute
Oh,
you
perfect.
pretty much when Charles comes.
Sweet. Thank you so much.
We'll be all set for that.
Awesome.
After you, do you know?
After me, there's a break. So then I think the next three will come and check. Yeah. Oh, I'm gonna grab my water.
She's all set. Presentation mic. We'll unmute your mic right as it turns, and then we'll.
Right, because my introductions are brief, but
Yep.
it's good to be heard.
No problem. Yeah, exactly. It'd be good to get on there.
Yeah. Okay, so we got about a minute.
I'm excited. Yeah. Yay. I know. It's crazy. Thanks. It's been.
So I'm going to start up at 2:20 naturally.
Okay. Perfect. Thank you. I appreciate you keeping to schedule. That's good.
If you don't do it carefully, you get out of whack.
Yeah, and I mean, I had two people who just walked in to see my presentation, so it was really, I was happy.
get started, please? Hello? Okay, very good. Our third speaker of the afternoon is Aurelia Balkanski, and she's got quite a title here. Are you stronger than the UV ray? Hydrocarbon, UV destruction, and chemistry in astrochemical ices. You're on.
Okay, awesome. Yes. My thesis title is, Are you stronger than a UV ray, hydrocarbon, UV destruction, chemistry, and astrochemical ices? But first, a bit of background. What are hydrocarbons and why are they important to this research? So hydrocarbons are small molecules made up of hydrogen and carbon atoms, in the name, of course. But they're also essential building blocks for prebiotic chemistry, which means they're some of the simplest organic compounds that serve as foundational structures from which more complex organic molecules can be built through various chemical reactions. So they're essentially like the Lego bricks of organic compounds. And they've actually been detected in the ISM, as well as in comets and protostellar and protoplanetary environments. And in the ISM, these hydrocarbons can undergo processes such as freeze out, upon which these volatile hydrocarbon species in gas phase can actually condense onto frozen icy grains that are present in the ISM and form icy mantles. So they essentially get trapped onto the ice and therefore can travel past their typical snow line. So they're really important to study to understand the chemical composition of the ISM. However, they can also break down due to UV radiation, which is present throughout the ISM. And so we really want to understand how they survive in these harsh interstellar environments and which molecules break down and whatnot. And so throughout this, we hypothesize that the chemical viability of small hydrocarbons is dependent on each specific molecule as well as the surrounding ice environment. So the experiments we run are with three main molecules, three main hydrocarbons, and these are the smallest hydrocarbons with more than one carbon. So they're slightly more complex than hydrocarbons such as methane, CH4, but they're still very small. So we work with ethylene, ethane, and propylene. And in my experiments, I also add in two experiments from Electra, thank you, Electra, with two larger hydrocarbons, benzene and toluene, and these are aromatic hydrocarbons, and they sort of symbolize what some of these smaller hydrocarbons can combine into and form. And these are really directly essential for prebiotic chemistry and can later form essential pieces of life like RNA and other macromolecules. So we run experiments with these 5 molecules pure in the lab, and then we take just ethylene and propylene, and we run additional experiments in matrices with xenon and with oxygen. So in xenon, we have an inert matrix, and in oxygen, it's an active matrix. So we really want to test how these molecules behave in different environments. And with the oxygen matrix, we're actually introducing the addition of new pathways for chemical reactions because our molecules can actually interact with these oxygen molecules. So that's an overview of the experiments, but how do we actually run them? Well, we do so in the Oberg lab. So this is an overview of the chamber and the whole entrapment that we are working with. Looks pretty complicated, but to sort of point out some of the important pieces. Number one, we have the ultra-high vacuum chamber. This is built to mimic the conditions of the interstellar medium. So it is super, super cold and super low pressure. And above it, the cryostat is actually what works to cool it down. And then 3 and 4 on either side, we have the IR spectrometer and the detector to actually take measurements on our experiments. Below the gas line where gases are created, and then they're dosed through number 6 into the chamber. And then, of course, none of these experiments would be possible without the lamp. So this is how we irradiate our molecules and hit them with photons. And then sort of a look a bit inside the chamber. Here, the substrate, which is where we dose our gas onto, is turned to face the lamp. So this is when we're hitting it with photons. But the substrate, even though it's not ideally drawn in the picture, can actually rotate 360 degrees. And so when we take measurements, we actually turn it so it's perpendicular to the IR and can take the measurement through there. And so the way this works is we take our gases, dose them into the chamber, and then hit them with UV photons to cause them to break down and study how this breakdown happens. And the way we actually measure this is with vibrational modes of our molecules. So here is an example of vibrational modes of ethylene, but basically every molecule vibrates in a specific way that can be measured in the IR. And so with ethylene, this ethylene molecule can vibrate in a C-C stretch, moving in and out. The hydrogens can stretch out symmetrically and asymmetrically, And then there's also bending. And each of these vibrational modes translates to a specific wave number in the IR that is unique to that molecule, so in this case, unique to ethylene. And we can look at it in the IR spectrum and say, okay, for example, this peak here is indicative of a CH stretch of ethylene. And when we destroy our molecules, these peaks in the IR will go down and they disappear, and new peaks form that belong to different molecules as they are forming. And so how this actually looks in some of our experiments. First, we have a zoomed-in view with the main vibrational peak of ethylene on the left. And as you can see, over time, as fluence increases, the lines get lighter. So we start with an initial concentration of ethylene, and then as we hit it with more photons, the ethylene is destroyed. And as this destruction happens, there is actually a formation of another molecule, acetylene here in this case, and it grows as fluence increases. And so then to zoom this out, this is an example of our pure ethylene experiments, which I'll get into a little bit later, but sort of just an overview of how this looks. This is kind of what we had before in the original picture with the original amount of ethylene. The pinker lower line is before any irradiation, before any UV photons hit the experiment, and then the purple line above is the last measurement taken with maximum fluence to sort of see what new peaks have formed after this irradiation. And I'll get into that a little bit more later. But basically, an overview of our experiments. We're working with some smaller and some larger hydrocarbons. And we take these first 5 hydrocarbons and run them in pure experiments. So we irradiate all of these. And the way we do is we look at how these initial peaks of these hydrocarbons decrease over time as we hit them with radiation. And so we fit a Gaussian underneath and kind of measure this decrease over time. And then we can plot them against each other. So here we have listed toluene, benzene, propylene, ethane, and ethylene. And these molecules are actually listed in the decreasing size of the molecule. So toluene, benzene, and propylene are some of the larger molecules, although propylene is on the smaller side. And then ethane and ethylene are smaller. And as we can see, destruction actually matches to the size of the molecule. So as we see here, toluene, benzene, propylene are basically not destroyed, whereas ethane, we see around 46% destruction, and ethylene all the way up to 63%. So from this, we can conclude that the destruction of a pure molecule increases as the size of the molecule decreases. Now, those were our experiments with just pure molecules, but we also take ethylene and propylene and look at them in matrices, so with xenon and with oxygen, of course. So to run into these, first we have, this is just pure ethylene and pure propylene, but when we introduce a matrix and actually complicate sort of the experiment and look at how destruction is affected by this, we see increased destruction in matrices with xenon and with oxygen in both cases of these molecules. And we can actually, in this case, we measure how quickly this destruction happens and can actually calculate the photodissociation rate of these molecules. So the way we do that is with this equation. And we take the initial concentration of the molecule, we have the rate constant, which is what we are calculating, and the decay plateau, J, is where it tapers off and destruction stops. And so we can fit lines to each of these using that same Gaussian fit shown before and actually get a measurement of the photodissociation rate for each of these molecules. So here with pure ethylene, we have around 63% destruction and a photodissociation rate of around 3 × 10 to the negative 18th. And this destruction increases both in rate and in amount when oxygen and xenon are introduced as the matrix. And this trend also continues with propylene. We have a fit here of propylene in the initial destruction, and then the destruction rates increase with oxygen and xenon. One thing I do want to point out here with pure propylene is, as you can see, and as was shown earlier, there's kind of an apparent dip and resurgence of propylene. We believe this is due to the restructuring of the molecules due to the irradiation, which kind of shifts the wavelength in IR. And is sort of messing with how this shows and how much of the concentration there is, which is why we'd only fit the initial destruction for our photodissociation rate, and we look at just the end to see what was left at the end of our experiment, which is about only 1% of the molecule was destroyed. Now, as these molecules are getting destroyed, things are also forming because they break down and these atoms that are floating around can recombine and smaller molecules can recombine. So we look at first the recombination of, or the products created through pure propylene. So here, as we saw, there was very little destruction, and thus there was very little chemistry that happens. So we see only about 2 peaks forming that are different from the initial baseline pre-irradiation. And one of them we have identified as methane, CH4. Then this changes a lot when we introduce something into the matrix. So first we have with xenon, in an inert matrix, xenon does not interact with these molecules, but it still increases destruction, as we've seen. So we see lots of products forming as these break down. And this continues as well with oxygen. The one important thing to point out here is because oxygen is an active matrix, it opens new pathways for chemical reactions with these molecules. So we can see all the products here are actually products with oxygen involved, sort of showing that like the presence of oxygen not only increases destruction, but also increases chemistry, and there's a lot of oxygen in these products. And so then finally, just a big picture of some of the experiments we ran. As I said before, hydrocarbons are really important for prebiotic chemistry. They're really the building blocks of life. And we want to understand how they survive and their viability out in the interstellar medium to understand where we might find them in the interstellar medium and the makeups and compositions of planets and stars. And as we saw through our experiments, the bigger the molecule, the stronger it is. So bigger molecules, and specifically pure molecules, break down a lot less in the under IR. But this isn't actually really realistic. It is rare that we'll find pure molecules out in the ISM. They're much more common in matrices and these smaller hydrocarbons, which is why we test them with smaller ones and in matrices. And so we want to understand here that while we do see a lot of destruction of these molecules and in their matrices, it is not complete in most cases. And so this is important for understanding what is left over from this and what can actually form during this time through star and planet formation in the ISM. And that is all. Thank you.
Thank you very much. So we have time for questions. Well, I have one. When you were showing the introduction of oxygen and xenon with the propylene, you actually got slightly more destruction with the xenon, which suggests that it may not be a chemical process at all. It's just having something big to bat around.
Yes, this is true. Both of these, like the difference between the destruction of oxygen and xenon in ethylene and with propylene is they're pretty statistically close. So we kind of counted them as about the same. But what we think is happening here is, number one, this xenon experiment was actually cut off a little short. So that is one thing. But also here we see so many products forming with the or fewer products forming with the oxygen in propylene than with ethylene. So we think that like this product formation accounts for a lot more of the destruction in that case.
Okay, thank you. Any other questions? Brandon.
Yeah, maybe somewhat related in the naive question on my part, but if you're showing everything in proton points from the lab, is there a change in this curve if you introduce pauses, if you stretch out that exposure time, or if you have big gaps in that exposure time? So are the metastable things that would interfere and add extra error in your result?
That is a really good question, and definitely something that could be included in future work. At this point, I don't really know. The way we did our radiation was we took measurements it was just as constant irradiation in this case, and then took measurements every 15 minutes for the first hour, and then every 30 minutes. So in that case, we were just kind of tracking destruction over time. But I would say, based on what we've seen here and how the destruction does taper off, sort of at the end of this irradiation time, which is about 3 hours, I would say that pauses probably don't have an effect because it's actually the photons directly being introduced to the molecule that break it down.
Brian? Yeah.
Could you say again, what's the cause of the constant term there that causes you not to go to zero?
I don't think that there's a direct cause of this constant here, but it's just sort of where the decay plateaus, and basically anything that can form has formed, and like even though there's more radiation, basically the molecule doesn't completely break down, but there are some molecules left over.
Can I follow up on that?
Go ahead.
So you're breaking apart these molecules, and then you are left with these very reactive pieces. Do they not want to come back together? Like, is this an equilibrium?
So basically I think this is best explained maybe with the pure ones. what happens is with the larger molecules, it's a lot harder for them to, like, as these molecules break apart, these larger molecules break apart into really, like, not realistic, relatively big pieces. And so it's harder for these bigger pieces to move away quickly and, like, move further away from each other sort of in this chamber. Whereas smaller pieces, they're smaller and they can kind of move faster, kind of like a little kid running through a crowd. Whereas, like, larger pieces have a lot more to push away. And so this destruction and recombination happens almost instantaneously. But these bigger pieces, when they break apart and it's only, for example, propylene in the matrix, and they can recombine. Whereas propylene, when you introduce something else, I'll go to the side, into the matrix, it's propylene, but there's also, for example, xenon in the way. And so as it breaks apart, these xenon particles actually kind of get in the way and push them further apart. And that's what stops this recombination and makes it more.
And you saw methane, but do you ever see any other molecules just appear, new molecules?
In just pure propylene, we have one molecule that I was not able to identify in the scope of this project. But with
Where is that?
right, oh,
Okay,
this, yeah, over there. And this is just basically through cross-checking the literature and seeing what has been available there. But with when xenon is introduced into the matrix, lots more things have formed. And I guess one thing, now that I'm holding this slide up here, that I will point out is there are a few products with oxygen, even though there was no oxygen introduced into the chamber during these experiments. But I did, as is written in my thesis, if anybody wants to read it, actually quantify the amount of carbon dioxide and carbon monoxide created. And it's low enough and like low enough monolayers that we actually believe it was just kind of left over and background oxygen in the chamber. But the rest of these products are due to the breakdown of propylene and ethylene.
Okay, Qijia, did you have a question?
Yeah, no, great presentation. I was wondering, like, how much, like, xenon or, like, oxygen you introduce, like, with respect to, like, the main hydrocarbon?
Fantastic.
And, like, how did you choose that?
Amazing question. Okay, yes, I probably should have mentioned that. We introduced them in about a 1-to-10 ratio, so the hydrocarbon 1 and the oxygen around 10, to kind of show, like, to mimic what conditions would be like in the interstellar medium and copy this. The one thing I will point out is oxygen and xenon as matrices are not actually very common in the ISM, but we chose these as sort of extreme test cases to say how does an inert matrix versus an active matrix affect the destruction of the molecule. But 1 to 10, good question.
Okay, thank you. So we have a little time for a break. We'll restart at 3 o'clock.
Thank you.
for Italian.
Here, we have a few more minutes, guys.
Okay. I'm gonna get some water. Sweet.
Just lost the screen. Oh, it's back.
So the mic it's on.
Okay.
Yeah, so it's outside. Should do just attach it.
Yep.
Up here. I'll just here so that's. Just to get a little slack. I don't think it'll slip.
Okay.
Put it right here too. If you want.
Yeah, maybe just so it doesn't fall.
Don't you have to move around at all?
Um,
In the middle, you're going to want
sure.
to point to something in the screen, so you should be able to put that in the pocket.
okay, I can do that.
Yeah.
Yeah.
And you told me once before, I want to correct pronunciation of your name, Edgar
Onate.
Onate.
Yes.
That's actually what I was thinking.
Perfect.
Title.
I believe it's. Oh, it's not showing up on here.
It's okay, don't worry about
258.
it. Okay, great. So,
Just make sure.
okay, once you get your screen. Yes. Okay, folks. Yeah. Okay, you two. Thank you. Okay, we're in for our second group of three, and it's a very different sequence of talks now. Very interesting all the same. So our speaker today is Edgar Onate, who's going to talk about using machine learning to identify and analyze asteroid families. It's a case of the Flora family. You're on.
Sweet. So welcome everyone. I'm going to be presenting my thesis on using machine learning to identify and analyze asteroid families, specifically talking about the case of the Flora family. So we all know and love asteroids to be rocky objects that are located mainly between Mars and Jupiter in the asteroid belt. And here we have an image that has that was taken by the Sphere and IVT 3D image software, where you can see a lot of large asteroids. And we know asteroids to be remnants from early formation of the solar system. And today I'm specifically going to be talking about some asteroids that are believed to be fragmented from larger bodies that broke off during collisions. So here we have an example of an asteroid family named Karma. So as you can see, it starts off as one larger asteroid as a parent body. And then eventually a collision happens, and it breaks off into many smaller pieces of asteroids. And essentially, these asteroids all are within the same family because we know they have the same orbital dynamics. So there's two kinds of asteroid families. There's fragmented and there's catering. The biggest difference is the size of the asteroid that initially collided and the size of whatever asteroids are left over. So with fragmented, you end up getting a more even distribution of the asteroids that are left over, whereas with cratering, you get a smaller impactor, which leaves a bigger parent asteroid that ends up having a crater. So by studying this, we can kind of see a chronology of the solar system, and we can kind of tell what kind of evolutionary process has happened. Yeah, so like I said, we can examine the solar system. We can talk about its evolutionary processes and the history and its formation. We can also talk about the origins of life on Earth. It's believed that asteroids contain the organic compounds that once collided on Earth and gave us the life we have. So it's also important because we can trace that back and use that chronology to trace back what kind of composition these asteroids had. And then as we saw in the previous image, some of the asteroids can deviate from their orbit and kind of head into the near Earth region. And so it's also important because we can reduce the risk of collisions and create these strategies to see whenever there's going to be a collision course with Earth itself. So here we have a plot that's pretty important in asteroid family research. It's the proper semi-major axis on the x-axis and the proper sign of inclination on the y-axis. These are proper elements of the asteroid families, which are essentially just orbital parameters of the asteroid families. Asteroid families should have similar proper elements to their parent, and so we can plot these things against each other and kind of see the groups of asteroids. So like black is the background asteroids, blue are the resonances, and then the rest of the colors are different kinds of families. Typically in classification, we use the hierarchical clustering method with the proper elements, but the HCM has a lot of limitations. It requires a lot of manual intervention and a lot of different kinds of parameters that eventually change the outcome that you get. So for example, whenever you use higher ejection velocities, you tend to get older families, but if you use lower ejection velocities, you get much younger families and a much more conservative view of what kind of families you actually have. The HCM is also limited because it doesn't have any ability to take in physical properties. We also don't have as much information on the physical properties of asteroids, but that's something that will hopefully increase as we have more observations happening in Gaia data and things like that. So the machine learning was basically one of two different ways we attempted. We tried supervised and unsupervised learning. The biggest difference between the two is that with supervised learning, all the data is labeled. And so you essentially know going into the algorithm what you should get. Whereas with unsupervised learning, you have unlabeled data. Both of these have pros and cons to them. For example, with supervised learning, a really big pro is because the data is labeled, you have sort of an idea of what the outcome should be. A con, for example, is because the data has to be labeled, it's much more computationally expensive and much more difficult to deal with in that sense. We have unsupervised learning has a lot of pros and a lot of cons as well. One of the pros is that since the data is unlabeled, there are a lot of patterns that are underlying that only unsupervised learning would be able to see and that the human eye wouldn't be able to see as well. But a con is that because it's unlabeled, it varies a lot on the parameters that you set. So you can get very different results based on just very different parameters that you decide to input. So it's a lot more versatile and volatile in that sense. So like I said, the HCM is the #1 way we use to classify asteroid families. It's the most conventional way. There are 4 types of linkages. So there's single, average, complete, and ward. This is an example where you have the same data set over and over again, all using the HCM algorithm, but using different types of linkages, you get different results as to what is and isn't classified as part of a family or not. And like we said, there's limitations with older families like Flora, because they're more dense and they're harder to track over time. And because they're more dense families, the HCM uses a distance metric between observations. So the more dense the family is, the harder it is to control that distance metric and not have some sort of chain effect going on when you end up classifying the families. So we started with unsupervised machine learning. And like I said, it has no information as to the asteroids that are labeled. So here we tried to use the Vesta family, where the right-hand side is a heat map of where we know the family actually is. This is information we actually know already. But we tried to use unsupervised learning to see if these algorithms could also classify Vesta as a family. And as you can see, each of those points is an asteroid, and each of the colors is a family that it was classifying. So obviously, it was unable to accurately classify the asteroids into a family. I also ran other algorithms such as HDBScan, DBScan, and optics, which are pretty popular in unsupervised machine learning clustering. And so, yeah, we realized there was too many limits to the asteroid family clustering with unsupervised machine learning, and then turned back to the supervised machine learning. And then we also realized that there was a family that could use a lot of this work to kind of solve a problem that it's had, and that's Flora. So Flora is an old and large asteroid in the main belt. It is very normal. It's an S-type, which is a very typical asteroid. And it's the biggest problem that Flora has is it's very ambiguous in the literature about whether or not it actually is a family. There are a lot of research papers that show that it's a family and has a certain amount of members, but there's also a lot of research papers about families that fail to even mention whether or not Flora is a family. So here we kind of came up with the question about whether or not machine learning could help identify whether Flora truly is or isn't a family. Being able to classify older families like Flora is super, super important because we can use this as like an example to use with other older families or more dense families that also exist and that are ambiguous in literature. So I ran two different supervised algorithms, one being K-neighbors classifier and one being gradient boosting classifier. This is the best results for K-neighbors classifier. So K-neighbors essentially looks at K-neighbors. It's a parameter, hyperparameter that's chosen by us. And then it finds the most common class and measures the distance between that, and then finds the nearest neighbors depending on what kind of input I decided to use. So I ran several different sets of parameters previously on families 4 through 20, so that's 4 different families, as kind of a test to see what kind of accuracy I was getting with different sets of parameters. Once I managed to get a couple that had higher accuracies, I then tested those on Flora data. So this is Flora data. This is a confusion matrix, which is really, really popular in machine learning. Essentially, you have true positives, which means we predicted that an asteroid was a part of Flora and it actually was a part of Flora. We have false positives, which means we predicted it was a part of Flora, but it actually isn't a part of Flora. And then false negatives means we predicted they weren't a part of Flora, but they actually are. And then true negatives, meaning we predicted they weren't a part of Flora, but they actually weren't a part of Flora. So obviously green means good and red means bad. We found that 11,500 or so tended to be the number of members with K-neighbors classifier, which is sort of similar to what other papers have found that do identify it as a family. And then the reason we have 90,000 true negatives is because we ran this over all of the asteroids, essentially. So this was our highest accuracy. It was 95% for the K-neighbors classifier, but we still managed to get better results with gradient boosting. So gradient boosting essentially starts with a model and then trains new models iteratively to fix the errors of previous models, so it's just constantly improving. Once again, we have much better results here, an accuracy of 98%, and actually, when I ran the parameters of gradient boosting, different kinds of parameters, most of those also tended to have higher accuracies than the K-neighbors classifier. So here we see that we have 13,000 members, which was a typical number with all the gradient boosting algorithms, and far less false negatives and false positives, which is good because it means there's less asteroids that we're falsely predicting. So ultimately, we do find that Flora is a family that exists in the main belt with around 13,000 members. And so yeah. So then after working with the machine learning, we realized we still needed to understand what was wrong with the HCM method and what was wrong with unsupervised learning in general. And so we thought to compute its age, because that's something that we read about a lot in the literature, and wanted to see whether or not we could find that same age, or whether or not there was a correlated explanation with why it wasn't working with the HCM and unsupervised learning. So we started by doing albedo calculation. I used WISE and NeoWISE data and proper elements that were calculated by David Nisvorny. Essentially, the albedos are used whenever you do the age calculation, so I had to do this step first. I started by taking all the NeoWISE and WISE data of Flora, and then reduced it to the good WISE data, which essentially just means I took the albedos of Flora and then the albedo error. And if the albedos were greater than or equal to 3 times the error, then they were used. And then these 4 on the right, the top 3 are a range that we set based visually on how the plots look, which I will show in a second. The bottom one is using z-score. Z-score is just like, it indicates whether a data point is above or below the mean. So we used a threshold of 3 for that one. So here are the plots for the albedo. So initially we started with all the Flora WISE, NeoWISE data, and then eventually we get to the ones that are cut off at certain ranges. As you can see, the pink dotted line is the albedo of the actual asteroid, the parent asteroid of Flora. The red dotted line is the mean of whatever step we are in the data reduction. As you can see, it's supposed to be kind of like a Gaussian, and that just makes sense because you start with the parent asteroid and then get less and less of certain asteroids with certain albedos as you move out. So we wanted the mean and Flora's albedos to be as close as possible. And you can also see in the top 3 plots that you end up getting this sort of spike on the left-hand side in albedos, which doesn't make much sense in terms of how Flora should be. And we attribute this to Baptistina, which is another family that is within the same proper element dynamical space as Flora, which I will show more about in a second. So we moved on to computing its age using these albedos. These are V-shaped plots. They're really cool. Essentially, if you plot the semi-major axis against the inverse diameter, you get a really, really cool characteristic V shape where the vertex or the point of the V is actually the parent asteroid. And then you can use the slopes of the V to calculate the age of the family. The only major difference between this V shape and other V shapes is the inner V shape that you see in kind of both of the plots, but it's really highlighted here. So that's actually Baptistina. So yeah, the asteroid at the corner of the V is Baptistina, which tells us that within this proper element space, Baptistina and Flora kind of have an overlap. So we took the slopes of both sides to calculate the age. And as you can see, the left-hand side of both of these plots kind of cuts off, and that's because of the resonances. So using the slope on the left-hand side, or we call it the inner side, we got an age of about 1 billion years, which is typical and what we found in the literature. But then whenever we took the slope of the outer side, we found the age calculated to be 2.5 billion years, which makes more sense with what we kind of had predicted about the family being too dense and too old to properly calculate with unsupervised machine learning. So it's really important to do this kind of work because the LSST at the Rubin Observatory hopefully will soon be observing the sky over and over again for 10 years, and it's supposed to generate approximately 20 terabytes of data per night. It's going to hopefully find many, many different asteroids that we have never seen before, and so we're going to need a way to classify these families in a much quicker way than with previous methods. So machine learning will hopefully change the way that people classify families. The solar system object population is super large, and so the older methods won't work, and then we might get older families, even older than Flora and such. So later down the line, it's ideal that we can classify these families at the press of a button with machine learning, rather than having to do it the old way. Also, as I mentioned, physical properties aren't currently taken into consideration, but hopefully we can add these as our knowledge increases with Gaia data releases and things like that, as well as spectral properties. So that's my time. So I'm just going to leave you with these conclusions. And yeah, thank you.
So do we have any questions for Edgar? Matt?
Yeah, I noticed in your confusion matrix that there are more false positives than false negatives.
Yes.
Why is that?
So there are 2 other values that I was going to add to, or I initially had on here. They're called precision and recall. They're also super important in machine learning, but we didn't take them into consideration, which is why I didn't add them. Essentially, precision is taking the true positives divided by true positives plus false positives. Recall is taking true positives divided by true positives plus false negatives. So essentially, if you want to increase your precision, or if you want to increase your recall, you kind of have to see which one of these 2 you want to be increased or decreased. In this case, we had a much higher recall, which is why in both cases, we have much less false positives. It's really a preference kind of thing, whether or not you want to identify more asteroids accurately but have a more conservative results, or if you want to be open about how many false negatives you have and things like that. So it's a value you can kind of choose and play with.
there consequences? If it's big or small, false positive, false negatives?
Yeah. I think in this case, it doesn't necessarily have any consequences just because the albedo calculation was almost separate from what we did with these values. Whenever we did the K-neighbors classifier and gradient boosting, we used all of the data, whereas with the albedos, we were doing the data reduction, which hopefully got rid of some of these false positives and false negatives.
Any other questions? Well, I have one. What does the word old mean in this context? Because I think you thought 1 billion years was old, but the solar system's 4.6 billion years old. I mean, so it looked like a youngster to me.
Let me see if I can find it. Yeah, so in the context of asteroid families, it is one of the older families. And like I said, a lot of the papers in the literature that we read had an age calculated of about 1 billion. So the fact that using this outer side, which we believe to be a little bit more accurate, found more than double that, tells us that it's way older than we initially believed. So yeah.
But is there some risk that the families become less and less distinguishable as they get older and older?
Yeah, so
you might not pick them up.
Yeah, so that's a little bit more like intuitive. So like as time goes on, the asteroids are going to spread out more, and then it's going to be much more difficult and to kind of keep track of which one of those are in the proper element space. And then there's also a chance of like more collisions and things like that. So the older a family is, the harder it is to kind of trace back that chronology.
Okay. Josh.
What's the albedo versus age relation? What's the physical cause? Space warming, I assume, some sort.
Oh, yeah, so not exactly sure what the relation is, but essentially we took the slopes by using a linearly square fit of the V-sides, and then having these different albedos could be plugged in, and then we find an age for the families.
Okay, I think there was another question, Jacob.
Oh yeah. So are all asteroids parts of asteroid families?
That's a good question.
That is a good question. I don't think so. No, because there's a lot of asteroids that just haven't collided with anything. So yeah, as far as we know, I don't think all of them are. You can see in this plot, this one here, like all these black ones are background that aren't a part of any families. So as far as we know, no, not all of them have to be a part of a family.
Thanks so much. That makes sense.
Okay. Any further questions? Let's thank our Edgar for a very interesting talk. You look like you know what you're doing.
I do. It's already on. I think it's already on. Nope. Hold on. I'll bring that back. All right.
Okay, let me introduce you. Okay, so our next speaker is Victoria Ono. She's done a project called Debiasing and Diffusion, Probabilistic Reconstruction of Dark Matter Fields from Galaxies.
Thank you. Hi, everyone. Thank you so much for being here. My name is Victoria, and today I'll be presenting to you a little bit about the research that we did on building a diffusion model to probabilistically reconstruct dark matter fields. And I've been fortunate enough to be advised by the wonderful Dr. Carol and Yang. So first, I'd like to start with our motivation here. Some of you may be familiar with cosmological simulations, but essentially they help us understand the structure and evolution of galaxies in the universe by modeling a variety of physical processes over time, and they've been able to reproduce many observable galaxies and model dark matter behavior with defined initial conditions. And in particular, hydrodynamical simulations more accurately model the galaxy formation process to help us understand the relationship between these observed
galaxy distributions and the underlying dark matter fields. Now, there are two challenges that come with this motivation. First is that if we just look at one simulation, that is not sufficient to cover the inherent uncertainties of the astrophysical processes or the cosmological parameters that were used in that simulation. And as the structures of the galaxies are also dependent on astrophysical processes such as gas cooling, star formation, stellar feedback, there exists a need for a variety of hydrodynamical simulations to model these different processes and to make predictions about the observable universe. But due to the limited resolution, these simulations usually adopt this coarse-grained subgrid models, which means that they're just describing these small-scale astrophysical processes, and in that there's a lot of large uncertainties lying in those models that lead to different kinds of predictions made by different galaxy formation simulations. The second challenge is that there's been significant progress made in machine learning in recent years, and cosmologists have taken advantage of that to reproduce the dark matter fields from stellar maps in these cosmological simulations. But they've used deterministic models, which means that they cannot describe the uncertainties that are assumed in the galaxy formation models. And luckily, there is a solution for both. So the first thing that I'd like to show you is this video right here is from the CAMELS project. So CAMELS is a suite of thousands of different numerical simulations, and they implement these subgrid physics models of illustrious TNG, Simba, and Asteroid. And as you can see here, given initial conditions that are different, over time, the structures of the universe start to look very different from one another. And this precisely shows why it's not enough to rely on a single simulation to find what dark matter fields might look like in a given volume. So that's a solution for our first challenge. And now I'd like to get into the second challenge, which is more interesting. The machine learning models fall into two different categories, deterministic and probabilistic. And in this case, we can build a probabilistic model to quantify the uncertainties in these galaxy formation models, which provides us with richer context on what we know and don't know. And so this is what I focused on in my project. But first, to really understand how the deterministic models can be a limitation, I started that as our baseline to see where that limitation lies. So this is a deterministic model that I've implemented, and a model that's commonly used for computer vision tasks is what's called a convolutional neural network, or CNN. So the one that we implement is called the UNet, which you can see by the shape of this graph, with the schematic here. It repeatedly takes in an input of an image, and it repeatedly downsizes the shape of that image. So if we start out with 256 pixels, then it makes that smaller while increasing the number of features or the information about that image. And so that happens in what's called an encoder or contraction path. And then at the bottom is what's called a bottleneck layer, which is where they retain only the most important information or the features about that image. And then it kind of reverses, and by upsampling, we end up with the same dimensions that we started out with, which is, again, 256 by 256 pixels. So here, our input is the star density field, and what we want to get as our output is the underlying dark matter field. So the objective of this model is to minimize the reconstruction error between the model's prediction as well as the true output of the dark matter density field. Now, the results from that is as shown here. On the left, we have from the simulation, the star field, the star density field, and then in the middle panel is the true output, or the underlying dark matter density field. And then the one on the right is showing you the prediction, or the model's predicted image of what the dark matter field might look like. And as you can see here, yes, it's doing a pretty good job in that it's predicting all the large filaments where that corresponds to the dark matter halos, or just where the stars lie in the input field. But it's not doing so great of a job of predicting the smaller filaments, where there's actually more dark matter particles, but aren't being captured in the prediction. And this is because of the fact that the model can only output the average of the target distribution. What this means is that because it's deterministic, the model can only have just one single output. And that means that of all the different kinds of possibilities, even if there's a target distribution of the dark matter fields, which is what it truly is in the underlying simulations, the model cannot do that because they're only able to just take the mathematical equation that's underlying it in the convolutional neural network and output a single image that is the average of all the different predictions. So the smaller filaments end up getting end up being smoothed out or just disappearing, and that's why we get this blurry version of the true output image. And so that is the deterministic model. Now, before we get into the probabilistic model, I'd like to just take a moment to give you some background context. And I'd like to start with DALL-E. So who here has used ChatGPT? Great. What about DALL-E? Oh, OK, a lot more than I expected. So if you're unfamiliar, DALL-E is a text-to-image model that generates realistic images from textual prompts. So here, I prompted a ChatGPT with our input. I would like to draw a picture of a group of astrophysicists at the CFA in Harvard listening to a talk on dark matter mapping, which is this one. And then this is what it gave me. But of course, the presenter is male. So then I was like, no, I want the presenter to be a woman. And they were able to give me a few more images, one of which ended up being one with the women, which is exactly what I wanted. So great, this is what we wanted, and now you might be wondering, all right, this is really cool and all, but what does that have to do anything with our motivation here? Well, this is what is known as a diffusion model, and that's exactly the type of model that my project uses. So what diffusion models are is that they're a class of generative models, the term generative AI coming from that, that can be used to generate new images. And in this particular algorithm, we have two processes. One is forward and one is backwards. So the forward process is a fixed process in that given an input or given an image that we want to reconstruct, which is the dark matter density field that we see here far on the left, it gradually adds noise in each time step, described by the subscript T here, and until we end up eventually ending up with a pure noise. So at each time step, it's going to add a Gaussian noise. So this is just fixed Gaussian distribution, and it's going to become more and more noisy until we get to just an image just purely of noise. It has nothing to do with dark matter density field. But what this helps us now is the reverse process. So in the reverse process, this is where the training actually happens. So we start with the capital T, or the final time step, and we go backwards until we want to get back to time step 0, or where the original image lies. And to help with that, in this model, we actually use what's called a conditioning, which represents the textual prompt that I put it in ChatGPT. We give the model a stellar density field, and then with that conditioning, the model learns by updating the parameters in what's called the unit architecture, which is exactly the same neural network that I trained in the deterministic model, to end up with a noiseless image of our true output. So again, the stellar density field corresponds to the textual prompt in DALL-E, and then the dark matter field corresponds to the generated image from that prompt. And so what I mentioned briefly is in this reverse sampling, reverse process, the neural network that is trained it's exactly the same architecture that I used in the previous deterministic model. And so as you can see here on the left side, now we actually have something a little different. So in the deterministic model, we just had the stellar density map, but in this case, because we're sampling from backwards from the noisy image to a less noisy image, this happens in each time step given a stellar density field as a conditioning, as well as this noisy version of the dark matter field. So that's our input, and then it's going to go through the same downsampling and upsampling process, and it's going to end up with an output that represents a less noisy image of the corresponding dark matter field. And this happens in the same T time steps until we get to time equals 0, or the starting point, which is the reconstructed dark matter field. And so the result of that means that, as you can recall, DALL-E gave us two different images when I gave a prompt. And similarly, from the same conditioning, which is our stellar density field, we can have different samples. And so that is a key to our solution for the second challenge that we started out with. it allows us to see what kinds of distributions are possible given one stellar density map when the noise realizations are different. And so what that means is that we have that true target distribution of probabilities distribution. So that each time the model takes in this input, the output can be slightly different because it is sampled from a probability distribution. It can sample from the mean or from some of the tails of the probability distribution, but each time it's going to look slightly different. But as you can see here, these are actually pretty similar. You can't really see eye to eye like how different they are. And that's a good sign because that means that the model is confident. And so now I want to show you some more results with the help of some more generated images. Now we have, again, a similar set of panels. The trained samples are, we start with the start density field. We have in the middle the true dark matter density field. And the one on the right, again, is the prediction from the model, but now I'm going to call it a sample because it's just one of the samples and one of the many predictions that it can have. And you can already tell that this is very different from what we had earlier in that it looks sharper, it's not blurry anymore, and it actually has the smaller filaments represented in the sample as well. And I want to contrast that again to the what's in the box, what's in the pink box here, what the deterministic model gave out. And so compared to that, the sample is actually much more accurate. However, I also want to show you the two other panels that you see on the bottom here. The middle lower panel shows the posterior mean, which means that what we essentially did is I just sampled a bunch of times from the same conditioning and averaged out, took the average of all of those different samples. And that is the posterior mean. It's taking the average of all of those different predictions. And you can see that that looks very similar to the deterministic model result here, and that's because that's exactly what the previous model was doing. And then I also want to show you the posterior standard deviation to kind of highlight that the darker the regions are, that means the model is more confident. So you can see the larger filaments or where the stars are, they're much darker because they're more confident. So the standard deviation is much lower for that. And to show you that from a different kind of angle, we wanted to see, okay, we have this entire field, but we also want to see, is it actually predicting great results for different subregions in a given volume? And so what we have here, you might not be able to see the circles too clearly, but we just picked out some of the regions, some less dense, and some more, has more stellar particles. Here, I'm just going to define the stellar mass or the mass region as the sum of the pixel values because that's essentially what they are. And we wanted to see, okay, is the model able to predict like the actual mass or the sum of the pixels in each of these regions? And you can see from the histogram here, the lower the masses are, the less accurate or the less confident the model is. And that's because in the star density field, the pixels are sparse, and so they're not able to be super confident about what the underlying distribution is. But as the masses get higher, there's definitely more pixels present in the dark matter field as well. So the standard deviation or the width of the distribution gets narrower and narrower. But you can tell that the solid lines represents what the true mass count is. This model is able to still predict overall, but on average, the actual mass count of each region. Now, these are all visual representations. I wanted to also see the summary statistics of that. So we start with a histogram. Overall, what does it look like? And then it's showing that it's actually able to have the accurate densities. We also have a power spectrum, which is to check if it has the right spatial distributions across the different scales. And then lastly, we have what's called the cross correlations, which means that if a data point increases at that pixel, does the other point also increase? So if it's closer to 1, that means that those sets are close to each other. And here, anything above 0.8 in general in statistics for cross correlations means it's really good. Here we have something more than 0.9 across all of the scales. So the model is able to predict really well. And I realize that I'm running out of time, so I'm going to go through the other results pretty quickly. We also did something called testing beyond the training set. So CAMELS has 3 different simulation suites for hydrodynamical. We tested 3 different models, Illustrious TNG, Simba, and Asteroid, and then tested across all the different combinations. And visually speaking, they do really well. And quantitatively speaking, the cross correlations also do really well. Interestingly, Asteroid trained model does really well for any of the other testing sets. And then lastly, what we did was to test on a larger volume. So we had about 500 times the volume of what I trained, and it's still able to predict overall really well. So this is a summary that I'll leave you with, and I also want to take the time to acknowledge my advisors as well as the graduate students that I worked with. This project could not have been made without them, so thank you so much, and thank you for listening.
So questions? Annie, you have a question.
I do have one. When you were showing all the different images, like especially also when you were showing the 3 different plots with respect to your challenges number 2, that slide, They're true that they're visual like very similar, but sometimes I can see that there's a kind of a halo in between the 2 main points, and sometimes it gets filled up and sometimes it doesn't. Like, see in the first one, there are like more filaments in between, and the other 2 is not. So I was wondering if it was possible to decide what parameters were like giving the different images, like what type of sampling of the Gaussian was giving you those solutions that would represent best the plot that you had on the left, like the image.
So the model doesn't have any other information other than the stellar density field and the dark matter field. So it really depends. It's really about the fact that the star field is pretty sparse, and so where the small filaments are, there just aren't really any pixel values there, and so the model kind of just has to take a guess, and so that's where the probability distribution arises and kind of just generates points sometimes, sometimes doesn't.
Go ahead.
I don't know how many of the stellar density images you used, but did the probability distribution change at all when you used different stellar densities, or was there like sort of a restriction on what kind of stellar density maps you had to use or didn't have to use, or was it?
I'm not sure what. So we trained on a simulation set that had different kinds of. They actually had like different astrophysical cosmological parameters, but they were just images that we fed into the model. And so, yeah. Sorry, I'm not sure how.
I guess my question is, whenever you had different kinds of images that you were using, did any of those images produce different kinds of probability distributions?
So we don't actually have like the probability I don't have like the probability distribution, what it actually looks like. We just have the different sampling images that we can just sample from the model, given the parameters that the model ended up having at the end of training. So no, I guess the answer to that would be no, because overall it was so. Actually, this panel might show you that the last one shows you that the model was able to kind of just marginalize over the different kinds of uncertainties and get a very similar distribution across all.
So you trained on the star map from the simulations, which I think goes down to a pretty low stellar mass level for the galaxies.
Mm-hmm.
Do you have an intuition for how things change if you were to restrict yourself to a brighter and brighter, or a more and more luminous or massive sort of floor on the detection? Because real samples just can't get down to the faint levels that these simulations probably reach. So I'm just kind of trying to get a feel for how things would behave if you were limited only to the brighter to the bigger galaxies.
I think it would do well, because the problem here was the fact that the star maps are sparse. And so I think if we had actual bright galaxies, that would also correspond to the dark matter halos and some of those regions. So I think it might do well. But yeah, that's interesting. I think actually there was like a paper that mapped from like dark matter halos to something else recently. So that might be something to look at and see if I can answer that later.
To move on, let's take one question, but maybe keep it brief. Qijia.
Oh, so I have a question about what do you mean truth CPM? Is this inferred from observation?
So by truth I mean the set from the simulations, like from the CAMELS project. They have both the star and the dark matter representation. So the true means just like from that data set, it's the true image. Yes, they're all simulations because unfortunately we can't see dark matter.
Not that is true, but the other simulation is not true. Illustrates is also simulations, right?
Yes.
When you say truth, it's also from simulation.
Yes. Yeah.
Why do you regard that one as truth, but the other one? Do you know what I mean? Maybe I didn't phrase it correctly. Both are simulations.
Mm-hmm.
How do you pick one to say that's truth? Why don't you pick illustrates to say that's truth?
Oh, we just have the different kinds of test training sets. Each of those are true. Like for each set, the simulation images are true ones, and then the predictions are what the model outputs from given those simulation images that they were trained on.
Okay. I think we do need to move on. Let's thank our speaker. This great demonstration of talent. It's Hanyue Wang, galaxy clustering and squeezed multipoint correlation function with dark energy spectroscopic instrument. It's coming.
Hello everyone, thanks for coming here. I'm happy to present my work with Professor Daniel Eisenstein about galaxy clustering and the squeezed multipoint correlation function using the dark energy spectroscopic instrument. In 1985, scientists here at the Center for Astrophysics mapped the galaxies for the first time, revealing this remarkable stickman pattern. Nowadays, with many large-scale galaxy surveys, we have a much more comprehensive mapping of galaxy distributions. But the major idea remains the same. Galaxies are not randomly distributed in the universe. This clustering of galaxies provides important information into cosmology, structure formations through cosmic times, galaxy evolution physics, and the complicated relationship between galaxy and dark matter. The motivation of this work is galaxy clustering as the biased tracers of the underlying dark matter field provide important insights into understanding the larger structure of the universe. Many works have studied the two-point functions to describe how individual galaxies correlate with each other and occupy dark matter halos. But the relationship between galaxy and dark matter is complicated. Also, galaxies are special as sometimes appear very close to each other and group as multiplets, such as pairs or triples. Therefore, in this work, we want to go beyond the two-point functions to cross-correlate the galaxy multiplets with the general galaxy field in order to better quantify galaxy distribution as a complicated relationship between galaxy and dark matter. Here's the outline of my talk. I will start with the data samples we are using and how we use them to identify multiplets. Then I will introduce the clustering methodologies and present the results from our measurement. Then I will talk about the cosmological embodied simulations and how we use them to generate mock galaxy catalogs. I will present a comparison between simulation and observation and discuss their implications on the galaxy dark matter connection. There's a whole separate section of my thesis regarding this incompleteness problem, and we propose a potential machine learning-based algorithm to resolve it. Unfortunately, I probably won't have time to touch it during this presentation, but I'm happy to discuss more if you're interested later. Okay, let's get started. We use data from the dark energy spectroscopic instrument. The DESI survey is a large-scale fiber-fast spectroscopic survey that will make optical spectra of over 40 million galaxies and quasars in a sky area of over 14,000 square degrees, stretching over 11 billion of years into the past. DESI has created the most comprehensive 3D map of galaxy distribution to date, offering important information about the nature of dark energy, its effect on the evolution history of the universe, and other interesting cosmological probes. In this study, we make use of the luminous red galaxies from DESI Year 1 data. We choose to use the LRGs because first, they are bright galaxies with high priority during fiber sign, therefore we can get a relatively complete sample. And second, they're highly biased tracers of the large scale structure. Here we show the Year 1 footprint of LRGs, color-coded by how many times a certain portion of sky area has been observed, and thus is closely correlated with how complete the area is. To avoid missing galaxies in the identified clusters, we choose to focus on area with relatively high completeness, which is marked as a red circle there. Sorry, the red box there. With this LRG sample, we search for galaxy pairs with a line of sight separation less than 10 megaparsec, and further make sure the transverse separation is less than 1.5 megaparsec. And then we link these pairs together, utilizing a friends of friends algorithm to form the multiplets. Here we check the number density distribution from both the LRGs and the galaxy pairs as a function of the redshift. From the number density redshift relation, we observe that the distribution of pairs in the redshift space can trace the LRG distribution really nicely. At some certain threshold, the LRG number density drops off, while the pair density drops off more quickly, suggesting for increasing incompleteness and strong redshift evolution. We would like to limit our analysis to where the number density is approximately constant, so we further cut the redshift range to be between 0.4 and 0.84. And here's some quick recap of our data sample, together with a histogram counting how many galaxy multiplets we found. So among the 1.7 million LRGs in a scale area of 560 degrees, over 23% of them lives in larger galaxy groups other than remaining as the singlets. We found 14,000 pairs, 2,700 triplets, and 800 quads. So as we approach larger galaxy multiplets, it is worth noting that we're also losing a lot of number densities. After introducing the LRG sample and the galaxy multiplets, we can use them to calculate the correlation functions which describe the galaxy clustering. The most commonly used statistical tool to quantify galaxy clustering is the two-point correlation function. Mathematically, 2PCF describes the access probability of finding a galaxy within a certain separation of another, or in terms of density fluctuations, it relates the overdensity as two separate locations. In the real world, astronomers use estimators based on pair counts of galaxies to measure these autocorrelations. And here, we adopt the famous Landy-Sisley estimator, where D represents the data catalog and R represents the random catalog, which follows the survey geometry, but in which galaxies are randomly distributed. On the right here, we show the resulting two-point redshift space correlation function with each galaxy in the sample weighted by the incompleteness of the area and the survey geometry. We showed along the line of sight direction, which is the pi-axis here, we see clear signatures for redshift space distortions, which is not the focus of this thesis, but another interesting probe for structure formation. For our purpose, we integrate along the line of sight in separate RP bins to form the projected correlation function. Therefore, we ignore the anisotropy in the 2D measurements and only focus on the physical distribution in the real space. Now let's move to the exciting part of higher order statistics, the higher order correlation functions. Similar to 2PCF, an endpoint correlation function relates overdensities that end separate locations instead of two. What is special about our work is that we choose to evaluate the multipoint functions in the squeeze limit, with the illustration here showing the roughly the scale difference we're talking about. As the galaxy multiplets compared with a single galaxy resides in more massive halos, and more massive halos are more clustered, we would expect to see higher clustering bias for these larger galaxy multiplets. As we cross-correlate the multiplets as distinct objects with a general galaxy field, the computationally expensive multi-point correlation calculation is reduced to a cross-correlation between the multiplet field and the galaxy field. And in real world, we use an estimator, a slightly different estimator, to measure this cross-correlation with multiplets of different sizes, namely the singlets, pairs, triplets, and quads. We observed that there is excess clustering, so more bias, for increasing size of multi-galaxy multiplets, which also corresponds with more massive dark matter halos. For easier comparison, we further summarized the statistics by averaging over the large-scale correlation functions, so between 10 and 30 megaparsec, and to obtain the general cluster level for each. With these measured cluster statistics, we need to employ cosmological simulations to further understand the physics behind them. And we use Abacus Summit. Abacus Summit is a large suite of high-performance, high-accuracy cosmological embodied simulations with 25 base boxes containing more than 300 billion particles as a Planck 2018 Lambda CDM cosmology. One important thing to note is that these embodied simulations only simulate massive particles under the effect of gravity, so that the outputs are the halo catalogs. As we are interested in galaxies, there exists a gap between this matter density field and the actual galaxy distribution. So, how can we assemble galaxies into these dark matter halos? Here we introduce important framework of halo occupation distribution, which bridges the gaps between dark matter and galaxy connection. HOD is a probabilistic model that describes galaxy occupation based on halo properties, primarily halo masses. For the LRG tracer, the main expected number of central and satellite galaxies per halo is given as follows, and it's worth noting that we treat the centrals and satellites differently due to their very different physical properties. Now we have everything we need to construct a mock galaxy catalog. But wait a minute. As you probably remember, when selecting LRG samples, I mentioned that we want to focus on regions with relatively high completeness. Correspondingly, we need to be careful with the incompleteness in observation. When talking about the incompleteness problem, I really mean the intrinsic loss from DESI fiber assignment procedure, because there are only enough fibers for every galaxy, and only 70% of the photometric targets have been observed spectroscopically. And for example, if there are high redshift quasar in the field, the nearby it will get priority during fiber assign, and the nearby RRGs will not be observed. These will lead to like a triplet look like a pair, and thus introduce bias into our measurements. The good news is the DESI second generation MOCs are divided into two categories depending on whether the fiber assign incompleteness has been perceived. So we can do a calibration between these two MOCs. Here we see that the general clustering level from the complete MOC is always lower than that from a fiber assign MOC, which indicate a complete sample is tracing less massive halos. And we further correct this effect before relating to actual observations. Up to this point, we're finally prepared to compare the simulation with observations. First, we present the comparison between our measurements using Y1 observation and the official DESI second generation MOCs. The autocorrelation on the left shows that the MOCs are around 10% under normalized compared with observation, and thus they're used more for validation purposes on this slide. As our focus is to evaluate the methodology of higher order statistics, we cross-correlate the galaxy multiplets identified in the MOCs with the general galaxy field. The discrepancies seem to persist, seem to persist in these multi-point correlations, but they're not consistent, which point us to question whether higher order statistics can offer more information in galaxy dark matter connection. The discrepancy is unfortunate, so we further modify the simulation ourselves to adjust the HOD parameters in order to predict a consistent 2PCF with observation. And we found one, as shown here. However, as we continue to calculate the higher order statistics, the deviations between data and simulation start to occur again. And it seems like simulation traces less massive dark matter halos compared with the actual observation. As we summarize the statistics and put in the calibrations for incomplete observation, the HOD still fails to predict the higher order correlations as effectively as it predicts the autocorrelations. What might be missing here? We further question whether including secondary halo properties into the HOD model can improve the agreement between data and simulation. As we discussed earlier, HRD modeling mainly depends on halo masses. However, at fixed halo mass, galaxy occupation can also change due to secondary halo properties. Here we introduce two physically motivated extensions, one based on the halo concentration and the other based on the local environment. The halo concentration-based bias is related to the galaxy assembly history of the dark matter halo, and the positive value means the galaxy prefer lower concentration halos. While the environment bias is dependent on the local dark matter density field, and the positive value means the halos in less dense environment. We import these secondary biases separately into the baseline HOD and further adjust the parameters to produce a consistent 2PCF compared with the observations. Here we show examples of 3 HODs that can fit autocorrelation equally well, including either concentration-based secondary bias or environment-based bias that push halos in denser environments. We regard them as benchmarks and evaluate their performance with higher order statistics. We calculate the cross-correlation with galaxy multiplets, summarize the statistics on large scales, and put in the correction for the bias from incompleteness. And finally, we compare the higher order correlations from observation and the 3 different HODs marked with different shape on this plot. While all the 3 models provide a reasonable fit to the autocorrelation, their performance diverges when we go to the higher order statistics. We observed that incorporating secondary bias, especially environment-based bias, can describe the cross-correlations better. Importantly, when models yield similar predictions for the 2-point correlations, making it hard to differentiate between them due to statistical uncertainties, we argue that including higher order statistics can be helpful to break model degeneracies and offer more constraining power on the complicated connection between galaxy and dark matter. To summarize, multiplets have a very different clustering pattern than single galaxies and is very sensitive to how galaxies trace halos. We observe larger clustering bias for larger galaxy multiplets as tracers for more massive halos, and the incomplete observation will lead to higher clustering in the multipoint functions. We would like to highlight the potential of higher order statistics to bridge degeneracies in models describing galaxy dark matter connection. Physically, including secondary halo properties can describe the cross correlations better, and galaxies prefer to occupy halos in denser environments. Lastly, I hope to mention the exciting opportunities ahead as we're having more and better data. Well, our analysis is limited to the small red box, only have like 560 square degrees. Up until last Friday, DAISY has surveyed more than 10 times of scale area, also with a higher completeness. So with these data, can significantly improve the errors of our measurements and leads to more exciting analysis in the future as we enter the era of precision cosmology. And there are a lot of people I would like to thank for this work, starting from my advisor Daniel Eisenstein for his guidance and all his support throughout my undergrad career. I would like to thank Dr. Carolina Cuesta, Dr. Sandy Yuan, and Misha on their help with simulation, machine learning, and the correlation functions. And thanks everyone for being here, and I'm happy to take questions.
So do we have any questions? Please, in the back.
So when you plot versus the covariance separation, I notice a maximum in a lot of the curves. Is there a physical reason for this, or?
By maximum, you mean?
Like the curves go up and then
If we look at the correlation with quads here, I would say that's mostly statistical uncertainties because we don't have a large sample of quads. As we said, we only have 800. And that's also a reason why we limit the multiple size to be 4, not 5, as we're observing these larger fluctuations because we don't have enough samples.
Okay, but it's also, you plot R times WP.
Oh, yeah.
So, I mean, the curves are actually dropping really quickly, and we multiply by a power law to get it to be something that's on a linear scale.
Any other questions?
Is it also possible maybe something is missing in the log simulation?
Something missing
in the simulation, which leads to the discrepancy between observation and log.
Yes, it is possible. There's not a very recent paper, but It's discussing whether we use an embodied simulation of pure dark matter field plus a HOD like framework can actually trace an actual hydrodynamical simulation like illustrates TNG, because we're not considering all the complicated processes like galaxy evolution feedback. So there's a possibility that this simulation is just not good enough and the HOD framework is not enough to describe this. But because we're finding a very good consistency between the 2-point correlations, we're trying to understand whether the higher point functions can offer more information.
Federica?
What like the opposite way? So is there a way to reduce the uncertainties in the observations so that you can understand if they fit better with your model or not?
Yes, as we said, we're having more data.
Okay.
So that's the year 1 data release. Probably many of you know was yesterday. It was very exciting. And at the end of the survey, we will have roughly 25% more scale areas than what has been used in this work, which means we'll reduce the error estimation by like 1/5. So that's a huge improvement. And when the error bars become smaller, we'll have more constraints.
Michel?
Have you tried the other method of fiber assignment on MOX? I think it's dubbed AltMTL.
The fiber assignment mocks?
Yeah, I think there were not only complete mocks and fast fiber assigned mocks, but also AltMTL. I cannot really tell right now what it stands for, but still.
So we did a really simple thing here, as we're just saying, okay, if the sample is incomplete, what's the effect on the large-scale clustering? Also with a very small separate. Also with we summarize everything with a single data point. So that's just we correct for this effect and we hope it works. But for sure, it does not fully quantify what is going on if we're actually looking at the details of the fiber assignment. And I haven't used other mocks, but that will be an interesting thing to look at. And this is also related to my work of the machine learning part, that we're trying to reconstruct the multiplets from a neural network to get rid of the fiber assignment effect.
Okay, yeah, because I think, we've been finding some issues with fast fiber assignment, and probably, and it seems likely that AltMTL is better. I actually had another question. So like you were using the Davis-Peebles estimator for galaxy and groups like pairs, triples, quads, cross correlations. I assume that was to avoid the need to construct randoms for those things. So that makes me curious. Using the same galaxies as for galaxies, it didn't work, I assume, right?
Yes, the reason we use a different estimator here is exactly the reason you mentioned, so we don't need to construct a random catalog for the galaxy multiplets. But one thing I didn't mention is that when we actually do the comparison, I moved the actual autocorrelation estimator also to be this one. So it has been consistent throughout the whole work, and we also did a comparison between these two estimators on the autocorrelations, and they match pretty well with each other, so we didn't further bother thinking about the details.
Thanks.
Okay, thank you very much. I think let's recognize all of our seniors. Okay.